Here's something that I'd like you to think about. Since you guys are here, you can talk to a neighbor if you want, or you can just think about it yourself. But it does make for good discussion. I'm serious about that. What would the extreme value theorem say? What would the extreme value theorem say about this little graph? Maybe you're looking back at your notes, which is smart, but what would the extreme value theorem say? And again, if you want to discuss it, you can see if the person nearby is thinking the same thing. All right, now it's not meant to be a trick question, but it can be a little tricky on a Monday here. And that is meant to kind of be a hint. It's not supposed to be a trick question, but it can seem a little tricky. Do you think you have the idea? What would the extreme value theorem say?
So would they not be able to say anything since
That's exactly right. It would say nothing. It was really well said. It would not be able to say anything about this. Okay, there's some questions in your assignment where that's the answer. Okay, basically the extreme value theorem doesn't apply. Ready? I'm just going to change this up. I don't know if you're writing it down or if you're just watching. Just whatever you got to do. I'm just trying to get you to think. So this is like a whole different graph. Like it really is a whole different graph, even though I just made one little change. And I'm just going to kind of ask you the same thing. What would the extreme value theorem say? What would the extreme value theorem say? You feel like you have this one a little more assurance here? Because this time the extreme value theorem would apply. It would apply. So that means that there's definitely an absolute max and min. I kind of gave the answer there. There's definitely an absolute max and min. It's not supposed to be hard to see that this is the absolute min. Okay? But now I have one. And it's not supposed to be too hard to see that this is the absolute max. But now I have one. Okay? Now, if you're like, well, you had an absolute max before. Yes, but I didn't have both. So the extreme value theorem guarantees that there will be both. Okay? I'm not going to make you write an essay on it, but I find that sometimes students don't realize what it's saying, and it's supposed to be kind of simple. As soon as you close it up with endpoints, then you have an absolute max and min. Okay? And emphasis on both. I have both a max and min. Okay? Because before I closed it up, I did have a maximum. I just didn't have both. All right. Now, we, at the end of the last lesson, actually did a problem. And what I want to do is kind of pick back up with that concept where we're basically trying to find the extrema. Okay, now remember, extrema is just kind of a fancy word for maximums and minimums. But it is a word that I'd like you guys to be aware of. And so if I ask you to find the extrema, then we're kind of using this method. It's a method where we're thinking about critical points and we're thinking about endpoints. Here's a little function. 3x squared minus 14x. 3x squared minus 14x. Now, it's important to note that there are not any endpoints. There is not something additional that's missing right here. Okay? I didn't give it, so it's not there. What that means is that the endpoints, which don't exist, will not be part of our analysis, but I can still find the critical points. Okay, now the critical points, they're kind of the ones that you're going to get used to finding because they have everything to do with derivatives. And so you always do the derivative. It's kind of like the first really logical step here. Okay, and when you do the derivative, it doesn't have to be hard. Sometimes the derivative is easy, so don't overthink it. You want to set it equal to 0. You want to set it equal to 0 because that's a place where we have a slope of 0. Like I said, it's not a hard derivative, but make sure you get it right, right? Thank you. All right, so the derivative is 6x minus 14. I got to take my own advice. Now, when you set that equal to 0, you're actually finding the place where the slope is equal to 0. You know, you're actually finding like this extrema. Okay, that's really what's going on here. We're forcing it to be a slope of 0. Okay, but use some algebra. You know, add 14 and divide by 6. Add 14 and divide by 6 and get yourself a little 7/3. Now, 7/3 is going to be a critical point. That's because it was part of this analysis where the slope is equal to 0. Just so we don't lose track of it, although I don't think we can, but so we don't lose track of it, I'm going to write 7/3 as a point. And I'm kind of leaving that y value sort of blank so that we remember to go back and find it. Now, if there were some other points to find, you would continue this analysis. But as you're going to find out, there really are no other points because my derivative can't be undefined. You know, I should really think, can my derivative be undefined? But it can't. There's no 0 in the denominator. There's no like illegal math operation. And sometimes kids are like, well, what's up with this undefined thing? I don't get it. I promise it's part of the analysis and there'll be some times where it works. But again, 6x minus 14 can never be undefined. So there's nothing that comes from that. Okay, and as we already said, there's no endpoints. It's up to you if you want to write this down, but there's no endpoints. I just kind of want to make sure that you don't forget about them. So all we have is one critical point. And when it all boils down to it, that critical point is my only extrema. So let's find the rest of it. Let's find the y value. Okay, remember how to find y values. You just plug into the original equation. You don't have to show this work necessarily. I'm probably not going to show it every time, but I just want to make sure you realize I'm just plugging in 7/3 into the original equation. Okay, you can probably guess that sometimes students plug it back into the derivative, but we want the y value. Okay, now you could use a calculator for that, whatever you got to do. I did it already, and it comes out to -16 1/3. And it looks like I changed it to a decimal, which is kind of strange. I'm mixing decimals with fractions, but basically I'm fine with whichever way you want to do it. Okay, that's the y value. Even though we've only done a few of these problems, and I know we had a break over the weekend, the point behind this is to classify this extrema as a max or min. If you think back to the last example we did, we compared two numbers. We compared them, but I don't have numbers to compare. All I have is this one critical point. So what we have to do here is we have to sort of put on our thinking cap and we have to think about what this original equation is really doing. And what it's doing is what every parabola does. It's a parabola, right? So you can kind of visualize any parabola that's going to open up. And if a parabola opens up, then it's going to have a minimum. It's going to have a minimum. Okay? Here's the thing that I don't like about this. I don't like this because I'm not giving you the full picture. You say, why don't you give us the full picture? Well, that's in the next lesson, okay, which we will do near the end of the week. So what's happening here is we're starting a process that I'm going to help you guys continue in the next lesson. Right now, the best we can do is we can just kind of think about the graph. But I still want you to do that so that you can say minimum. It's pretty neat when I show you the next step. Okay, it's pretty neat because you guys will see how some things connect. We're just not ready for that yet, which is all right. Okay, let's continue with just this first step. The first step is to find the extrema. And I want you to get good at it, okay? Because once we get this first step figured out, then we'll be ready to move on to that next idea. Here we have x cubed plus 1. X cubed plus 1 from -2 to 4. Okay, now listen, our goal is to decide where we have extrema. They can happen at critical points. They can happen at endpoints. The critical points are going to come from the derivative, which again, it's normally pretty common. Kids will say, all right, I'll do the derivative, do it correctly. You get 3x squared. This time I'm sure of that, and set it equal to 0. When you set it equal to 0, you're forcing the slope to equal 0. You're forcing the slope to equal 0, which will give you a special x value. Okay, that special x value is the critical point. Or should I say, it's one of the critical points. Just to make sure I don't lose track of it, I'm going to make sure it gets in the list. Now, I know it's kind of weird, but you're supposed to also think about if this could be undefined. There's no way that 3x squared is ever undefined. Okay, there's not a fraction there. There's not some type of other illegal math, which we will do, but it just doesn't happen. And if you're like, well, why do you keep talking about that? Because it does happen eventually. And I just want to make sure that you don't forget that idea. But I don't get anything out of that. I don't get any other x value. On to the endpoints. Now, the endpoints, we actually could have talked about from the beginning because, well, there was a closed interval. And so since there's a closed interval, the extreme value theorem says that these endpoints are going to be part of the analysis. So we need to make sure that they make the list. It's not real hard to put them in the list. I just want to make sure that you don't forget about them. All right. Now, each of these missing y values, I kind of save that for the end so that you remember, or so that you realize that you just need to plug it back into the original equation. So we plug 0 back into the original equation. 0 cubed plus 1 is, of course, 1. Plug -2 back into the original equation. Okay. Do it carefully. Take -2 cubed, you get -8 plus 7, or plus 1 is -7. And then plug in 4. 4 cubed is 64. So now we have 65. I'll let you know that by the time we get to the end of this chapter, there will be a big no calculator push. And that's kind of what's going on here. I haven't really used a calculator for anything. The numbers are reasonable. Okay, and that will become true when you guys eventually get graded. So when you get to a problem in the assignment, don't be so quick to use your calculator. Just practice. Okay, and there wasn't anything real hard here that you would need a calculator for. Now, as you look over these numbers, I'm talking about the y values. As you look over these y values, you should be able to compare them. I mean, one of them is clearly the biggest. Okay, it's not supposed to be a trick. This one's the biggest. It's definitely then the maximum. And we want to say so. We want to label it. This one here is the smallest. -7 is the smallest y value. So this is the minimum. brings us back to our first point, 0, 1. Okay, now, just because it's in the middle doesn't mean that it's a none. Again, just because it's in the middle doesn't mean that it's a none. But it turns out that when you think about the graph, that 0, 1 isn't a maximum or minimum. In other words, it is a none. And I guess we have a little bit of we're not there yet. There's something else that I'm going to show you. And I won't say that ever. I won't keep saying that, but there's something else I'll show you that will help us to be able to look at this 0, 1 without looking at that graph. But right now we have the graph. We see 0, 1, and I don't want you to be fooled. 0, 1 is not a maximum or minimum. It's actually something else. That's something else we will figure out soon enough. Okay, so what can we do here? Two things. You could cross it off. You could say none. Just make sure that you kind of hear me out that soon we will figure out that that is something else. It's something else. All right. Now, let me give you a problem. See if you guys can take what we've done, which is basically thinking about some derivatives equal to 0. We also have some endpoints mixing in. But can you take that and can you apply it to this problem? Basically, can you find the extrema for 1/3 x to the third? Oops, check that. Just x to the third. Sorry about that. X to the third minus 1/2 x squared. There's your fraction. Minus 2x. Just to make sure you're not confused, there's no endpoints. I didn't forget them. There's just no endpoints. If you're doing the derivative, that's a definite yes. You want to do the derivative. If you're setting the derivative equal to 0, that's your next yes. That's good. Now, you guys are normal, which is probably good. Of course, normal is just kind of a relative term, but basically, you're doing something that many students have done throughout the ages. You're trying to solve this equation, but you might be applying, just to say nicely, you might be applying kind of the wrong technique. Some of you move 2 to the other side and you factored out an x. Okay, I like that you're trying to factor, but you can't factor unless the equation is equal to 0. So it's actually, we actually want to keep the minus 2. We want to keep the minus 2 where it is. Does that jog your memory? Does that jog your factoring memory? So you have to factor like a trinomial. You have to factor like a FOIL factor. Now, students throughout the ages have learned how to factor this type of thing so many different ways. It might depend on what teacher you had. It might depend on what you remember. I tend to go back to just the basics, like not necessarily like little tricks, but there's nothing wrong with tricks. If you learned how to factor this by drawing like an X, or if you learned how to factor this by doing like a British method where you did something with like arrows. Okay, again, we can talk about any of that if you need to, or you can just kind of fill in the numbers. Now, the numbers you fill in have to multiply to be -2. The only numbers that multiply to be -2 are like 2 and 1, but one of them is negative. You have to make sure, though, that when you check your answer, that this 3x and whatever number you put here times x, that they're going to check to be this number in the middle. So they have to multiply to be -2, and then these two arrows have to check to be -x. And so you definitely want to put a 2 here and a 1 here and make sure the 1 is negative. Okay, if the 1 is negative, that's going to give us a -3x plus a 2x. So that's kind of your factoring review. Keep going. If you didn't get that far, keep going. If you're trying to think about where you're trying to go, you're trying to go to the maximums and minimums. Remember, your goal is to find the maximums and minimums. I like that you're trying to do this without a calculator. I think that shows that's a good idea, but it's okay if you have to get a calculator out maybe for some of the math. Especially when it comes to trying to work out -2/3. I'd rather that you get it right. I want you to realize that these y values, they turn out to be pretty important, okay? The y value, even though it just comes from plugging in, when you get these two y values, oops, I have this backwards. Okay, so the y value that goes with -2/3 is 0.82. That was with a calculator. And then the one that goes with 1 is -1.5. If you're realizing that those y values kind of give you the final answer, you're right. Okay, we did all this calculus, but when it comes down to it, you're just looking at 0.82 and you're saying, okay, that's bigger than -1.5. So if 0.82 is bigger, then this is a maximum. And of course, -1.5 is smaller, so that's a minimum. Again, those y values actually kind of reveal the final answer, at least for now. Here's something that we can add to this problem. I want you to begin to realize that these 2 points, they're not only called critical points, but they truly are critical. They are important. Okay, because if you think about the graph of these points, you will begin to realize that they sort of describe our original function. It's actually pretty interesting that our original function can be thought of as really just these 2 points, because if this is going to be a maximum, right? I mean, that's what you said. You said that this is a max, then the graph would have to go up and then back down as it approaches that maximum. And if this is going to be a minimum, well, then of course it has to do the opposite. Now, what I did right there, if you really think about it, isn't too earth-shattering, but it's oh so significant. I was able to draw the graph by just thinking about the critical points. Okay, it's a place that we'll get to as we continue to explore basically this concept of using derivatives to analyze graphs, and again, right now, to analyze them for the maximums and minimums. Okay, that's a good stopping point.